Swinburne University of Technology.
All right, sounds good. So I'll be talking about Mathematica and astronomy. Now this is going to be a very broad topic, obviously. You know, there's really no hope of covering everything that Mathematica can do and everything that can be done in astronomy. So it will be a very broad thing where I'm going to be covering a lot of things. Unfortunately, due to time constraints, I won't be able to cover many of them in too much depth. So by all means, if there's something you want to stop and have me talk about in more depth, do feel free to interrupt and ask any questions. I obviously can't see hands, but if you just do want to shout out at any point in time, that's perfectly welcome, and I don't have any problem with that at all. As I just said, this will be fairly broad. I just don't have the time to cover things in much depth, but I will try and basically give an overview of the kinds of things that Mathematica is capable of, especially as it relates to astronomy and the physics-type topics, and mathematics as it's relevant to astronomy and physics, and why you might use astronomy to basically make your life a little bit easier. Before we get into Mathematica specifically, I do want to bring up basically products that Wolfram Research makes specifically, just so you're aware that they exist, because basically these things are accessible to you by and large already. So I'll be talking about Mathematica specifically. If you do have a cluster, which I understand you guys have, Grid Mathematica might be an option, but I did take a look at your web page, and the big problem with clusters can be things like the queue management system or your queue manager. And I understand that you guys are using the Torque queue manager, which is unfortunately a queue management system that we don't support at the current time. We unfortunately support Altair PBS, which is very similar but not Torque. We're looking at making Torque accessible. We kind of have some people working on that, so that might be something that's available in the near future. So you might want to keep in contact with us about that in the near future, because we've been able to get it to work in some cases but not others, is basically the short of it. So I'm not going to be talking a whole lot about getting things to work on doing HPC right now, because I don't think it's actually worked for you at the current time, but maybe in the near future. But I will be talking about Mathematica. Mathematica does have built-in parallelization capabilities that I do want to mention if you're doing coding. So you can parallelize on a single computer. You can make things like ad hoc clusters using Lightweight Grid Manager, even if you're not using Grid Mathematica. Another product that you already probably have access to is Wolfram Workbench, just so you're aware that this exists. So if you are doing something like serious coding in Mathematica, Mathematica does have its own IDE. So if you're writing large code bases in Mathematica, it's built on the Eclipse IDE, if anyone's familiar with coding in Java. So if you want to do things like breakpoints and things like this, that's perfectly possible in Mathematica, and you can get a product to do this that's available to you already, most likely. But moving on to Mathematica specifically. So the idea behind Mathematica is that we don't have add-ons or anything like this, or we're constantly asking you guys to give us more money or anything like that. You already have all these areas of functionality built into Mathematica. And so this is actually just a screenshot of the documentation center, where you can basically, as you move into a new area or as you want to do something in Mathematica, all that functionality is already waiting for you. And because we'll be giving such a broad talk today, I won't be able to cover everything in detail. So I do want to point out this documentation center that you can access is going to help, and then Wolfram documentation is really quite useful. So for example, if you're doing something like solving differential equations numerically, you might go to the NDSolve documentation, which is our numerical differential equation solver. And the first thing you'll notice about the documentation is that it's very useful in the sense that it's fully interactive. So instead of it just being a static thing that you can't interact with, you can come in here and you can type things, and you can actually evaluate things in place. So if you make a little modification to it, you add a coefficient, for example, you can just modify things in place. So this is a very nice, useful thing that you can do. It really helps people learn things faster. The other nice thing here is that it's very much in-depth. So if you just want to use, for example, this function as a black box, it certainly tells you how you can use it as a black box, where you can just kind of throw equations into the numerical differential equation solver. But if you want things in more detail, there's a lot of detail in here as well. So for example, There's a tutorial at the bottom here, for example, advanced numerical differential equation solving. And if you really want to read about, stiffness testing in general, there's sources being cited, and there's just a lot of detail if you really want to read about the nitty-gritty details of this kind of stuff. So the Documentation Center, it's there, it's useful, it's interactive, it's probably a lot better than the documentation in a lot of other languages, and so I really do encourage you to be aware of its existence. Okay. The other big advantage that Mathematica has over a lot of other environments is its basic interface. So right now I'm actually giving this presentation in Mathematica itself. So this is basically this environment that I'm in right here. This is just a Mathematica notebook itself. So you can do things like you can give presentations in Mathematica. You can write code in Mathematica. It has basic debugging features in it. You can write reports in Mathematica. So if you open up a Mathematica notebook, by default it's kind of in a coding environment where you can evaluate code. You can write loops in Mathematica, so you can write like a do loop, for example, or whatever. But you can also write text. So you can integrate text where you can write, this is a text cell. You can do different kinds of formatting. So if you want, for example, a title cell. So the point is you can write entire things like reports or whatnot inside of a Mathematica notebook as well. This can include, as this slide right here shows, this can include things like text cells. It can include special kinds of formatting to that text, basically what you would expect from a word processor. It can include graphics. It can include typeset math. It can include code. It can include things like applications, and we'll talk more about applications later on. So it's a very powerful environment to do things in. And kind of completing this overview of Mathematica before we move on to specific functionality, Mathematica, what many people don't realize, they kind of picture Mathematica as basically an environment for one-liners maybe. Mathematica really is a full-fledged programming environment. You really can write code in Mathematica. So this is basically an example of the fact that Mathematica is actually a multi-paradigm programming environment. So basically this is a number of different ways where you can compute the factorial of some integer n. And you can see that it supports a number of different programming styles. So if you're most familiar with, for example, procedural programming, we're writing things like do loops, for loops, while loops. Mathematica certainly supports those. If you're more familiar with functional programming, so more similar to things like in Python, Mathematica is actually better to do functional programming in Mathematica. It's generally a little bit faster in Mathematica, and it supports just a number of different programming styles. People do write large code bases in Mathematica, like I said previously. Mathematica does have its own IDE for supporting these large code bases. People have written things like hundreds of thousands or even millions of lines of code in Mathematica. And just as a note, the programming language that's behind Mathematica is called the Wolfram language, if you ever hear that, that term kind of bandied around. People do actually do this kind of thing. Yes, and so that's a good note from Craig. So, people have written things like testing environments in Mathematica as well. Now, of course, a very important thing if you're doing things like writing code in Mathematica is that you have to be able to, it's nice to have a nice isolated piece of code, but, in addition to having an isolated piece of code, that code has to be able to talk with, other pieces of code, things out there in the world. So it has to be able to talk with data. It has to be able to talk with other pieces of code. And so to that end, Mathematica code does play well with others. It has what we call link technology, where it can speak with things in other languages. So for example, it has a technology called MathLink, where if you have code that's written in C or C++, it can communicate with that code in both ways. So if you have a C program and it needs to call something in Mathematica, you can do that. Or if you have a Mathematica program and it needs to call a program written in C, you can do that communication as well. You can also do communication with things in the .NET framework, with things in Java. If you're doing GPU programming, there's an OpenCL link for things in OpenCL, and there's also a CUDA link for CUDA programming. If you're working with data, there's a database link. So if you have like a SQL database, you can pull data in real time from that SQL database. So you can issue things like SQL commands from Mathematica to manipulate your database if you want, or you can manipulate that database using Wolfram language functionality as well. If you also want to manipulate Excel spreadsheets, if your data is tied up in Excel spreadsheets, you can do that as well. So Mathematica does play well with others, and so you can do that, and it's quite important to people. Of course, if you have data, it also might be tied up in files, so it is important to be able to import and export files. So, many of this is basically a list of file formats that Mathematica can import, and this is a list of file formats that Mathematica can export. And what this means is that basically you can just tell Mathematica where one of these files is. Mathematica can recognize that file basically based on its file extension, and they can interpret that data and bring it into Mathematica, and they can work with that data. So important file formats that you might be interested in is, for example, the FITS file format. So let's see, is supported. So for example, if you point it to a FITS file, Mathematica will recognize it, both the image and the header, and then you can bring that image and the header into Mathematica and work with it inside of Mathematica. Or for example, if you make something like an image in Mathematica, you can export that image as an EPS, for example, and then you could export it to something like a tech editor so you can write it up in a paper. So, when I was writing papers for, a journal, for example, I might actually make the image in Mathematica, export it to EPS, and then put it into a tech editor so that I could write it up for a journal article. And I've published papers with images that were actually originally created in Mathematica, for example. Okay. So that was kind of just a broad overview of things that can be done in Mathematica. So now moving on to kind of specific areas of functionality, beginning with doing actually numerics in Mathematica. So Mathematica is a very powerful numerical engine. There's kind of a rumor out there that I don't know why it got around that Mathematica is not very good at numerics, or it's slow at numerics, or something like this. I think that this might have actually been true kind of way back when, maybe in the 90s or something like that. But since then, roughly around the year 2000, Mathematica has rapidly improved there, largely because most of our numerics are based on the Intel MKL engine. So it's kind of a state-of-the-art numerical engine if you're not familiar with it. It's extremely fast at doing these basic numerical operations. And since we've kind of built everything on top of that, we're actually quite fast in terms of numerics. So just basic examples of numerics. Plotting is a numerical operation. There are numerical integrators, of course, so nintegrate is our basic numeric integrator, and it basically has access to a lot of these different numerical algorithms into it. So by default, what it will do is it'll basically look at your integrand and choose the most appropriate algorithm for doing that integral. But of course, if you want, you can override its default decision and force it to choose the numerical method that you would like it to use. There are things like numerical solvers, so if you want to numerically solve equations, of course you can do that if you want. So here's basically solving where curves are intersecting with one another, as represented by the red dots. There's a numerical differential equation solver as well, where we can visualize these solutions to a differential equation right here. And I'm just varying two parameters in real time and having Mathematica calculate the results of the differential equation on the screen right here. You can do these, and you can also do these calculations at arbitrary precision. So by default, Mathematica has kind of a default notion of what the precision should be done at. Mathematica is a arbitrary precision engine, so you can do the calculations at whatever precision you would like, if necessary. Of course, Mathematica is also a powerful symbolic engine. So this is kind of what Mathematica is best known for. It's a computer algebra system. So if you need to treat symbols, or you need to treat variables as symbols, Mathematica is very good at this. So just basic examples of this, algebraically expanding a plus b to the 20th power. So it basically does this. This is basically Pascal's triangle. If you need to algebraically solve this quadratic equation right here, okay, well here's basically the quadratic formula in a symbolic sense. It can do calculus symbolically. This is probably what it's best known for, as students are cheating on in their calculus course or whatever, where it can do things like indefinite integrals, definite integrals symbolically. And of course there's also, this one takes a little bit of time to do. And you can see it does have a notion of things like non-elementary functions, where it can both accept non-elementary functions as input, and it can also give results in terms of quite complicated and fairly obscure non-elementary functions in some cases. And you can also solve differential equations. So this is basically just a damped oscillator problem, and then you can vary the damping term and solve that differential equation analytically in real time right here. Now, kind of an important thing that many people miss right here is that if you can do something numerically and you can do something symbolically, you can actually do both at once, which can be a very powerful thing to do. So these are so-called hybrid calculations. So just as a simple example of this is, let's say you wanted to numerically integrate the ceiling function times the Bessel J function times this Bessel J function right here. Now, if you were to throw this into a typical numerical integrator, this would actually be quite difficult, because if you were to look at this at the integrand right here as a plot, you can see, okay, well, it's pretty nasty in that you have the discontinuities due to the ceiling function, and you have, you basically have different, oscillatory behavior in these different regimes. So that's a fairly nasty problem for a numerical integrator. So what you can do with a so-called hybrid calculation is that you can look at it analytically to begin with, and you can analytically recognize, well, okay, it's basically a piecewise function at the integers because of the ceiling function. And so what you should do is you should divide it up into 3 distinct pieces at the integers, of course. You should find different quadrature rules for each piece. And using those different quadrature rules for each piece, you should basically apply a different numerical integrator for each piece individually. Now, you don't have to do any of this by hand because Mathematica does all this hybrid integration for you behind the scenes. So all you have to do is call Mathematica's numerical integrator. It actually does the hybrid calculation for you behind the scenes, and does this integral properly at high precision, and does it very quickly. And so you might not even know that it's doing a hybrid calculation, but it's actually doing it very quickly and very accurately for you. And so if you were to throw this into your own numerical integrator or many of our competitors' numerical integrators, I think that this would actually take quite a bit longer because it is such a difficult thing to do with a purely numerical integrator. So these are basically just some examples demonstrating that, okay, it can be useful to actually hook these into Mathematica's visualization tools. So, basically you can just take some differential equations, you can throw them in. Oftentimes it's basically something like a realistic workflow in Mathematica. So looking at the Lorentz subtractor, okay, you can quickly solve them using something like an ND solver. You can quickly visualize them in Mathematica, and you can see if you actually visualize something in 3D in Mathematica, you can actually rotate it around. You can look at it at different angles. You can add color, and so you can study it very quickly. So basically what I've done is I've just mapped time to a color in this case, basically just using this little bit of code right here. So I can very quickly inspect it. Then because I have symbolic capabilities, I can very quickly take the derivative of this. So this is a numerical expression, but I can very quickly, because basically this gives me an interpolating function, I can very quickly take the derivative of this interpolating function. So Mathematica recognizes this derivative notation. I can very quickly take the derivative of this interpolating function, so I can quickly see, okay, what's the change as a function of time, and quickly visualize that. I can do things like I can take, okay, what happens when I take two solutions that are right next to one another? So here's the, the solution at 28, use 28.1 and 27.9, and I visualize those with different colors. So one of them's blue, one of them's red, and one of them's green. And so you can see, okay, that they deviate pretty quickly, even though they start off close to one another. By looking at them in different colors, they're fairly different pretty quickly. Or you can look at different trajectories using this method. So basically what I do in this case is I take the same solution, but I just look at 3 different trajectories with a particle that starts at slightly different places. And I visualize those trajectories in different colors in this case. And you can see, because the Lorentz subtractor is a classical kind of chaotic system, you can see that those trajectories diverge pretty quickly, as you might expect. So you can see this is a pretty simple workflow right here, not a lot of code in each step, and you can quickly visualize these things, make fairly attractive visualizations that you can inspect in 3 dimensions without having to do a whole lot of work. And so it's one of the real strengths of Mathematica, where you can do a little bit of math, numerically solve something, do a little bit of symbolics where you take a derivative, visualize something in a nice way, and do all that kind of within one environment and get a result very nicely and very quickly. You can also do, this is kind of new and improved in Mathematica 10, there's also a nice finite element framework. So this is a very kind of simple toy example. What you can do is you can basically just specify a region. So in this case I'm just saying, okay, let's take this little cylindrical region. I'll just define a simple operator, a little Poisson operator. And then you can just specify conditions along that, say Neumann conditions or Dirichlet conditions. I'll use Dirichlet conditions in this case. You can just once again throw those into ND-solve, and now Mathematica actually has finite element methods available to ND-solve. And so I'll just visualize those solutions. You can see that Mathematica has used finite element methods to solve the differential equation for this. Well, in this case, it's a simple finite element case, but you can of course do this for more complicated situations. So Mathematica is now a good tool for doing finite element analysis as well. As we've seen a little bit already, Mathematica is a powerful tool for doing visualization. So this can be two-dimensional visualization, three-dimensional visualization. You can do data visualization. So if you're plotting points, you can do this in two and three dimensions as well. There's specialized visualization. So if you're doing statistical visualization, you can do that. If you're doing wavelets, there's specialized visualizations for doing things like wavelets. If you're doing vector plotting, there's specialized visualization for this, etc. So just some examples of how specialized you can get. If you're plotting multiple surfaces, you can do those in multiple colors. And you can really get quite in-depth where you can make it very attractive things where you can mess around with things like the opacity of things. If you want to make things see-through, you can play around with lighting. So if you want to make lighting different colors, or you want to make the specularity act in a specific way. And by doing this, you can make quite attractive visualizations that are very customized. So Mathematica does have a default notion of how things should look, but if you want to override that and make very specific things, by all means you can do that. And especially if you're making things that need to be fit for publication, you of course do need to do this where you mess around with a lot of options, because things do need to be in very specific ways for publication. But you can do that within Mathematica without too much fuss. Mathematica is also a very powerful tool for doing statistics. So just in general areas, of course you can do descriptive and exploratory statistics. You can do model fitting, linear regression, nonlinear regression, generalized linear model fitting. You can do statistical distributions, work with those. You can do hypothesis testing, etc. So just as a very brief overview of this, let me bring in some data. So this is demonstrating how easy it is to bring in data from a file. So basically all you have to do is say, here's the import function, point it to a file, and it brings that data into Mathematica. So now I have that data in Mathematica. You can see what it looks like. It's basically just an array of ordered pairs of data. Now I can quickly visualize that data. So here's what the data looks like. And so the story behind this data is this is basically just reproducing Alex Wolfskam's original observation of pulsar planets from back in the early 90s, I believe. And so the basic idea is he was just doing some pulsar timing, where he took, so these are basically just, he has a millisecond pulsar, it's rotating very quickly, and so we just needed to fit a nonlinear model to this, where this is the nonlinear model that he's fitting to that data. And so there's a function in Mathematica for doing a nonlinear model fit that's called nonlinear model fit. So all you need to do is say, okay, nonlinear model fit this data with this model, where this is the independent variable, and then these are the parameters. We can see you're just specifying the starting point for the parameters that you're fitting. So what Mathematica does is when it'll actually do the fit, you can see it does it very quickly and efficiently. And now when you're doing this, you can see what it does. It actually gives you a fitted, what we call a fitted model object. And so you might ask yourself, okay, why is it giving me a fitted model object instead of just the best fit? Why doesn't it give me, why does it give me an object? And the answer is actually when Mathematica gives you this fitted, when it actually does this fit, it's actually giving you a lot more than just the best fit parameters. It actually, behind the scenes, is actually calculating all of these properties for you, and it's actually pre-calculated all of these properties. So it's calculated best fit statistics like the R-squared value or the AIC or the BIC if you preferred those fitting statistics. It's calculated things like ANOVA tables if you're interested in those. It's calculated things like mean prediction bands. It's calculated things like fitting residuals, which are going to be very important in this case, etc. So for example, if you want to know the R-squared statistic, you can just say pulsar fit, which is the name of the variable, and you can say R-squared, and that's that fitting residual right there, or that fitting statistic right there. And that's already been pre-computed. And if you want to know the ANOVA table, for example, you can just type in that, and you can see it gives you all that information right there. So it's, all the stuff has already been done for you. You don't have to do it. It's just sitting right there waiting for your use. So you can just visualize it right here, and you can see, okay, Mathematica has done a pretty good job fitting that right there. Obviously, the fit looks quite good when you plot both the fit and the data on the same axes. But now you can see what you can do is now you can say, okay, let's take the fit residuals out from the data. And you can see, okay, there are some fit residuals. They're quite small compared to the original data. So the original data had data that were on the order of unity, and the fit residuals are on the order of 0.02 or so. So the residuals are on the order of a few percent. So they're pretty small. And so kind of the original scientific point here was that these timing residuals are not random. They're actually systematic. And so these are actually the signature of the pulsar planets. So this would be the model if this pulsar was not accompanied by planets. But my understanding is that this is the actual signature of the pulsar planets. Let's skip over that. And so just as kind of one other example of a thing you can do with statistics in Mathematica is you can do things like hypothesis testing. So this is the guide page from the documentation of the various things you can do with hypothesis testing in Mathematica. So for example, if you wanted to do something like a Kolmogorov-Smirnov test in Mathematica, you can just say Kolmogorov-Smirnov test of whatever data set you have, and then Mathematica gives you basically the p-value out. So once again, these things aren't difficult to do in Mathematica. The function is basically there waiting for you. You just have to give it the data, and it can give you the result out. By default, it tests against the normal distribution, or a Gaussian distribution, which is why you don't have to tell it what distribution you're testing against. But of course, if you want to test against some other distribution, which you might want to do in general, you can provide a second argument, which will test your data set against an arbitrary distribution. If you want to use some other test other than a Kolmogorov-Smirnov test, there are things like Anderson-Darling test, Kramer-von Mises, and there are all these other things you can do with hypothesis testing. There's students' t-tests, paired t-tests, all kinds of things you can do, and these are all built into Mathematica already. So these are really just examples of things you can do in Mathematica with statistics. This is by no means comprehensive. Another big thing that's new in Mathematica 10 especially is machine learning. So this is kind of a big new thing that lots of people are trying to do with lots of different languages. And it's really been built in a nice convenient way in Mathematica. And in that there are just really two functions that you need to know how to use in Mathematica to do this, and those are the classify function and the predict function. The basic idea is that you just need to provide these functions a training data set, and after you've trained the functions, you can use them in some useful way. So as an example of this is basically just a handwriting recognition exercise. So in this case, the basic idea was that the U.S. Postal Service needed to be able to recognize zip codes. So what you would do is you would train it based on handwriting, where you'd say, okay, this is a picture of a 2, this is a picture of a 5, this is a picture of an 8. And so you train that data set just by passing it in a that set of data. And now you can go in and you can actually say, okay, now here's something we want you to identify, where we put in now actual data, and we ask Mathematica to actually identify what's in these images. And so you can see it says, okay, this is a 0, this is a 1, this is a 2, this is a 3. And you can see it's actually identified these, with the exception of a few of these where it's actually misidentified some of these because this isn't such a large training set. Now, and that's fine, because you can see, for example, this one, which is misidentified as a 6 because we didn't have such a large, or it's misidentified this 6 as a 4 because we didn't have such a large training set. But you can see, even when you do this, even though it tried to automatically identify it as a 4, you can do things like you can drill a little bit deeper and you can say, okay, well, what was the probability according to this classify function that it was a 4? And you can see that Mathematica was only 45% sure that this was in fact a 4, and it was 25% sure that it was a 6, and it was 24% sure that it was a 0. So in this case it wasn't so sure about it, and so if you're actually writing a real program based on this, you might take some other action if you were only 45% sure that it was something, because that's not such a high certainty. You can see in this case Mathematica automatically chose to use a logistic regression method to do this machine learning task. There are other methods built into Mathematica that it might choose to use, or you can force it to use. It might use random forests or naive Bayes methods or support vector machines, etc. Kind of one neat example of this that I always like to show people is that it can do this kind of image recognition thing in more depth. So one neat thing we've done in Mathematica 10.1 is we actually gave it a very large training set. We basically gave it a bunch of images, and we basically said, okay, this is a picture of a dog, and this is a bunch of pictures of cats, and these are a bunch of pictures of cars, for example. And so there's now a function that's basically built on the classify function called image identify, where just as basically a fun example, you can just give it pictures of things, like for example, let's do a kangaroo. So you can just say, okay, Mathematica, here's a picture, and so you can just say image identify of this thing. And then now Mathematica will just go into that image, it'll find the dominant thing in that image, and it'll say, that's a picture of a kangaroo. And so you can just take pictures of whatever it is, and using machine learning, Mathematica can generally identify pretty well what's in that image. It's pretty good at animals, it's pretty good at plants. Eucalyptus. Let's see if we can identify eucalyptus. I've never tried this one, so I don't know what's going to happen here. This is always risky. Well, I didn't get that one. It thinks it's a bay leaf, which actually looks pretty similar to eucalyptus, so that's not terrible. But you can see it does a reasonable job of identifying things based on its training data set. Now, of course, it's only as good as its training data set. I will say that I did try this with astronomical objects, and it evidently hasn't been trained on astronomical objects because I gave it a whole bunch of planets, and it didn't recognize any of them, and it returned ridiculous things because it hadn't been trained on them. So I wouldn't test it on planets, for example. Mathematica is also very good at optimization. So if you're doing optimization tasks, it can minimize things and maximize things. As an example of this, so here it's found a basic minimum. It can do this in many dimensions if you need to. So for example, here's doing it in multiple dimensions, and if you need to find that maximum, Mathematica can identify where that maximum is. So this is basically optimizing a 7-dimensional problem with a fairly complicated looking optimization problem. And you can see if you need to do this, Mathematica can solve it in, here's basically doing a timing thing, and Mathematica does this 7-dimensional optimization problem in roughly 0.09 seconds. So that's pretty good. Mathematica also has a number of specialized subjects, some of which might be relevant to you guys. So for example, you can do control system engineering. So in this case, I just designed a basic Kalman filter. So for example, you can design state space models. In this case, basically, I just created a sinusoidal signal and a little bit of noise to it. Basically, just define a basic Kalman filter and then apply that Kalman filter. Whoops.
Karl, if you allow me, just someone.
Apply that Kalman filter to the noisy sinusoidal signal, and you can see, okay, it cleans up that signal just fine. This is a very simple example, but you can design things like filters and whatnot using system engineering in Mathematica.
Karl, excuse me, there is someone joining us via phone and is keep talking. Can you please mute your phone?
Another area that might be important is you can also do image processing in Mathematica. So as we saw earlier, it's actually quite easy to bring images into Mathematica. You can basically, if it's just an image, you can basically just drag it into Mathematica as you saw from the internet. As we saw, and I mean if it's a FITS file, you can just basically just import the image into Mathematica using the import function. Once you bring an image into Mathematica, you can do a lot of interesting things with it. It's basically just a bitmap once you bring it into Mathematica, and you can do what you will with that bitmap. So essentially, you can programmatically manipulate it, but there are a large host of image processing algorithms built into Mathematica that can kind of automatically do things with that, as you might expect. So I'm just going to kind of mention a very brief overview of image processing things that you can do in Mathematica. But rest assured, there's a much larger range of things that you can do in Mathematica. So as very simple things you can do in Mathematica, of course you can do things like deconvolution, convolution, sharpen images. So here I bring in a blurry image, I deconvolve it, I try and sharpen it using kind of built-in things. So here I specify, okay, I'm going to deconvolve it using a Gaussian matrix, and you can see it does sharpen it up quite nicely. You can do things like image alignment. You can stitch images together. So there's basically just a function in Mathematica called image align, where you can it'll basically just try and automatically do everything for you. If you want to handle things in a little bit more depth, you can do things like geometric transformations on images. You can do things like perspective transformations. So in this case, I basically have an image of a picture of a city, in this case, from two different angles where there's some overlap between the two. And basically, Mathematica recognizes automatically where the different perspectives between these two. It applies a geometric transformation to them, as you can see with this matrix, and then it stitches them together. There's a function called image compose that stitches them together. And so I basically just colored them differently, where you can see this little rotation, stitch them together, and now you can see those two images together right here. You can also do things like an analysis of an image. So in this case, this is a biological example. So I have a number of cells, which are just these basic blobs. I just want to go through and I want to count how many cells are in the image. So this might be something you do in astronomy, where you need to count how many blobs are in the image. Very easy to do. You can just basically say, okay, here's my image. The first step might be to say, okay, I just want to make this a black and white image, and I want to fill in all the blobs. So I don't really care about the details of how they're filled in, just completely fill them in. Then I say, okay, I want to basically turn each one of these a different color, so basically number each one of these individually. And then I just want to count them, use something like a watershed transform, which is basically allows you to count them individually. So it's basically the algorithm that counts them individually. And then this select components thing is basically says I only want to count things as a component if it's a certain size, if it's between 500 and 3,000 pixels. So you don't count little things like this that are tiny as a component. And then it goes through and it says, okay, now I just want to measure each one. And so you can see I've numbered each one of the cells individually here with basically just 5 or 6 lines of code. This is just a slightly more complicated example, or a slightly more in-depth example. It's actually not any more complicated in terms of lines of code of the previous slide. It's a little bit hard to see because the little blobs in this image aren't very distinct against the screen, but there are a whole bunch of little blobs in this if you look at it from the right angle. And so this basically does the same thing, except now instead of the blobs being all circular, they're elongated. They are literal blobs in that they're ellipsoidal, or they're blobby. I wouldn't describe them as ellipsoidal actually. They are actual blobs, and not very circular. And so the basic idea is that with basically 4 lines of code or so, you can go through and you can measure, you can identify each one of these with morphological components. You can select them saying, okay, I only want to count things that are between 2 and 20 pixels in size. And now you can go through and you can say, okay, I want to measure the elongation, the width, and the mean intensity of each one of these. And you can create a histogram of each one of these. And so really with just 4 lines of code, you can go through and you can make intelligent measurements of all of these in a very simple way in Mathematica. You can also do things like edge detection. So in this case, I went through and I just took a basic picture of the Whirlpool Nebula just off of Google image search. And I might want to do something that's saying like, okay, let's detect the edges of this image. And so there's a function in Mathematica called edge detect. It goes through, and if you pick out the edges with the appropriate parameters, you can do things like you can find the arms of the galaxies, as you can see right here, which basically correspond to the brightest edges. And you can see if you choose different parameters, it'll actually pull out different features because basically the different radiuses and different thresholds that you pull out basically correspond to different features. So if you go into really fine things, you can basically pull out different types of structures. But if you pull out things based on this radius, it basically corresponds to those edges. So you do have a lot of control over these things if you wish. So as you've seen in a lot of these demonstrations, you do have access to dynamic interfaces in Mathematica. So, for example, here's a little dynamic interface where I simulate an electrostatic potential. Here's a dynamic interface where I just do a very simple, very simple little image processing demonstration. And one of the nice things about Mathematica is that these dynamic interfaces are incredibly easy to create. And these types of dynamic interfaces are extremely useful, whether you're making them for yourself to explore something like a data set or an image. You might be creating them for a class that you're teaching, or you might create them for your students, for example. You might create them for a report for your colleagues or something like that. And these things are incredibly simple to create. And so let me just demonstrate that real quick. So let's say that you had a simple plot that you wanted to create. Okay, so what I'll do is I'll just plot a sinusoid right here, or a sine function. Okay, so that's easy enough to do. And now what I want to do is I want to make this interactive. So how would you make an interactive plot in Mathematica? Well, the real mother function right here is the manipulate function. So all you have to do is you just have to wrap that plot function with the manipulate function. And you just have to give it some parameter to manipulate. So let's call that parameter A. And we'll just say, okay, I just want A to go from, let's say, 1 to 10. And so now you can see that Mathematica automatically makes the interface for you. It makes a little slider for you, and then it does that calculation for you in real time. If you want to make multiple controls in here, you can just add another parameter. Tell it what you want to do with that extra parameter. Let's say 0 to pi. And now it makes 2 sliders for you. So one of them is the phase and one of them is the period. And so it has some intelligent notion of how these things should be made. If you really want to get customized, you can actually override these defaults. So there are ways to kind of customize these things in a great deal of detail that you can read about in the Documentation Center. But by default, these things are actually pretty useful if necessary. And you can do things like making animations if you want to animate through these things, etc. So these things are really useful where you can put things like your data into these things and maybe overlay something interactive on top of them. And you can really explore what you're doing with these types of interfaces and to really gain intuition about your data or give them to your students if they need to explore something, some mathematical function, etc. And the really nice thing about these things is on the next slide here, is that if you need to distribute something like this to your colleagues, for example. So the big thing is that if you make something inside of Mathematica, the question has always been, if I make something inside of Mathematica, how can I give it to other people? because we're aware that unfortunately not everyone in the world has Mathematica. And so what we also want people to be aware of is that you actually can distribute things to people who don't have Mathematica. There is something that we call the CDF player, which is basically just a free Mathematica viewer, where if you give your viewers a Mathematica notebook, or you can save it as a CDF file, which is basically essentially just a Mathematica notebook, they can download the FreeCDF viewer. Now the FreeCDF viewer allows them to interact with your notebook. They can see your code. If you have any three-dimensional objects, any plots or anything like that, they can interact with your three-dimensional objects. They can rotate them around. They can look at it from different angles. If you have any manipulates or anything interactive like that, they can play around with the sliders just like this. They can do everything like that. Everything's still interactive. So unlike a PDF file, everything's fully interactive. The only thing they can't do is they can't create new content. So they can't write their own code within the CDF viewer, but they can interact with the content you created for them, essentially. So if you do make something in Mathematica, it's not impossible to distribute to people like your colleagues or to your students or something like that. You just have to tell them to download the CDF viewer, and they can still interact with any content you might create for them. Okay. So that was the whirlwind tour of Mathematica. So I'll leave the conclusions up here. I've left a little bit of time for questions and answers because I know that I'd have to go really fast, and I probably didn't leave much time for questions during that because I was speaking so quickly. But by all means, if you have any questions right now, or if you feel I left anything out, I'd be happy to take any questions that you might have about using Mathematica.
Thanks, Karl. So everyone unmuted now, so if you just want to ask questions, you can ask directly via voice or send it through chat.
Yeah, I believe that this is being recorded. So my understanding was that, so I actually do see a little thing that says this is being recorded. And then I believe that they said it was being posted somewhere. I don't have the details on that, but someone else can probably tell you.
Yep, so this has been recorded, and probably it will be on the Swinburne channel soonish, so probably within a week or something like this.
Yeah, and the other thing I do want to point out is, so I told you that a lot of things were possible, but I just didn't have time to go into a lot of detail about how those things were possible. So I do want to point out that if you're interested in actually learning how to do things, okay, there is a documentation center. But we do offer things like courses, so we do have like online courses where we'd actually go through in detail, and we have things like 4-hour courses where we talk about programming in Mathematica. We do have online, like on-demand videos about doing things in Mathematica. And so if you go to the Wolfram website at wolfram.com, and there's a section on education in Mathematica, that'll give you information about programming in Mathematica for when these courses happen. And there are also a very large number of on-demand videos where it'll actually go through and attempt to basically give you a little bit more detail on how these things are possible, instead of just having me tell you that they are possible. So that's probably a good resource for you to be aware of.
So, Karl, I have a question with respect to the visualization mainly in the neural network. How big is the data set that I can use to visualize or use with neural network? Is there some limitation? Is it based on Java or something like this, where I need a big memory in order to do this?
No, there isn't a strict limit with what can be passed into like a neural network or anything like that. It's basically what you can handle with your system's memory. So it's going to be memory and memory limited, basically. There's no hard limit on. So in general in Mathematica, there aren't many things where there's some hard-coded upper limit on the size of data. It's going to be generally limited by the available memory. Is by far the most common limit.
Great sense. So is there Other questions?
Okay, so what about Wolfram Alpha? Okay, so first, okay, so yeah, so I didn't mention Wolfram Alpha, but you can certainly, so yes, so as you're probably aware, there is this thing called Wolfram Alpha, which is another thing to make. The basic idea behind Wolfram Alpha is that if you're using the Wolfram language that has a very specific syntax to use it, if you use Wolfram Alpha, the big idea behind Wolfram Alpha is that you can just type things in a natural language inquiry. So you can ask, you know, what is the weather, and it will try and answer that. So you could type in weather, and it would, you know, provide a whole bunch of information right here. This does use the internet, so, you know, it does do an internet query, so it has to, you know, hit the internet, and it provides a whole bunch of information. It includes things like curated data sets. We have a whole bunch of curated data. It includes things like real-time data. So, you know, if you ask, you know, what is the, you know, where is the ISS? It'll probably include, hopefully include the real-time location of the International Space Station. So right now the International Space Station is actually pretty much right overhead for where I am, surprisingly. So, so this is pretty neat. So the basic idea is, so one thing you might want to be aware of, especially if you're teaching students, is, so if you're not aware of this already, you should be aware of this, is that many students use this, especially in the calculus courses, because they love to use this for doing their math homework. Integrate squared plus, I don't know. Because when you do this kind of things, it'll give you, it can do things symbolically, and they especially like this because you can press this button where it gives things like step-by-step solutions, and it can actually show the work, and it can be used to cheat on things like homework. So it's very popular among students for that reason. So you should be aware of that. Anyway, so you can integrate, as you can see, this into your code, and you can use this in Mathematica. There's a function in Mathematica called Wolfram Alpha, which basically allows you to call Wolfram Alpha from code in Mathematica if you wish. And if you kind of want to programmatically pull out some specific parts, so let's say you want to pull out this image right here, there are ways of programmatically doing that using this Wolfram Alpha function if so desired. There are kind of limitations on how often you can call Wolfram Alpha. So if you wrote like essentially a cron job where you called Wolfram Alpha, you know, 1,000,000 times a day, we would cut that off. But the limit is fairly reasonable, where you can call it a few thousand times a day, I think. As long as you're not calling it like every second, you can do that if you have Mathematica. Hopefully that answers the question.
Was Paola's question about the actual website Wolfram Alpha, or
right.
is it about using Wolfram Alpha API within Wolfram language?
Okay, yeah, I mean, so there is a so this is basically the website. So there is a website, wolframalpha.com, which basically gives you this. I mean, there is an API that you can use. That's not really covered here, but so there is a Wolfram Alpha API where you can, that I'm not hugely familiar with, but you can access Wolfram Alpha from programmatically, and there, let me see if I can pull this up. Oops, that's a typo. So the basic idea is that you can access Wolfram Alpha right here, as you can see. Individually, there's essentially bindings from a number of different languages. So if you do need to access it, if you do need to integrate it into, for example, your website or something like this, you can do this. I'm not hugely familiar with integrating, to be honest, as you can probably tell. I'm not hugely familiar with integrating Wolfram Alpha web services into random web apps, but this is allegedly possible.
I saw University of Western Australia, Swinburne, and CSIRO as attendees. University of Western Australia and Swinburne both have unlimited Mathematica license for both students and for faculty. CSIRO, I don't know. Well, there's many licenses within CSIRO, although there's not a distributed CSIRO license pool for all of the organization.
Yeah, I mean, I'm not. Craig could probably get back to you. You would either know that or could get back to you. That I'm not familiar with the licensing status of the universities in Australia, so Craig would have to speak to that. Yeah, I don't know if he knows off the top of his head either.
No, I just said, did you hear that University of Western Australia and Swinburne have unlimited, and all their students are accessed to unlimited or Mathematica.
Yep.
And CSIRO, which is on the call as well, they have licenses throughout CSIRO. And I can't specifically talk about the department that each individual's in, but I'm happy to. If you want to drop me an email to craigb@wolfram.com, I can investigate for you.
Okay.
So any other questions? Okay, if not, let me thank Karl again. Thanks for your time today, and thanks for the great introduction to Mathematica, and we hope we will have other webinars later on with more details about visualization and neural networks and things like
This has been a Swinburne production.